Unless you
Alright, let's start discussing. This is chapter 6. Stability. Okay. So when we were discussing chapter 5, what I told you guys was time response this is categorized into transient response and steady state response. Okay. So from this point onwards, what we do is we try to discuss steady state response. We have discussed all the characteristics, all the relevant characteristics, parameters of transient response. We'll now start discussing steady state response. Okay. So again, steady state response would be the response after the system goes into steady state. For example, when you're flying, what would be the steady state? Which part of the response would be the steady state response?
Cruise.
Once the plane starts cruising. Okay, that's good. When it is taking off or when it's landing, that is, when it's taking off, that's the transient response. You can think about it like that. Okay. So, stability, we've already discussed stability. Okay. How do you define what would make a system stable? What discussion did we have which related to stability? When is a system stable? Think about the second order systems. What are the four categories of second order systems?
Critically down.
Huh?
Critically down. Under down. And on down.
And critically down, right? Are all these systems stable?
No.
Which one is not stable?
On down.
Undamped is what?
Unstable.
Huh? It's marginally stable. Okay. So if you think about undamped, everything else is stable. Critically damped is stable, underdamped is stable, overdamped is stable. All those are stable systems. And what is the characteristics? What is the property of these? What made them stable? What?
Settle at something.
No, but what determined their stability?
The zeta.
Mathematically, what was that stable thing we discussed? What made mathematically stable?
Zeta? The zeta ratio?
No. So what we discussed was, remember this, all poles, that is roots of denominator, roots of denominator of transfer function. Lie in the left half plane. We will call this LHP is left half plane of SP. Okay, if you do the pole plot, so just recall this. For an unstable system, where are the poles? For an undamped system, where are the poles?
Poles are on the undamped straight
Undamped system.
W.
They are on the j omega axis, right? So this, if the poles are here, this is a undamped system, purely imaginary. This undamped is marginally stable. Okay. All the other system poles are in this half. So underdamped, overdamped, critically damped. All the poles are in this half. So you see, left half plane of this S plane. Okay. The system is stable only if the poles are in the left half plane. If the poles are in the right half plane, the system is unstable. And there is no, we don't discuss control, we don't discuss automatic control for an unstable system. It doesn't make sense. Okay. You C of T.
Everything to the right is unstable. Everything to the right of the pole.
If the poles are in the right half plane, the system is unstable. Okay? The poles means roots of the denominator of the transfer function. On right half plane, the system is unstable. If C of t is a time response, generally what we saw was C of t is equal to C of t, it can be divided into n plus c f of t. One, this is the natural response. So we have seen this, and this is the forced. Okay. So what we saw was, what causes this forced response?
The force response is
It's because of
the input.
the input. So everything other than the force, if there is no input, the natural response should be decaying. Okay? It should be, we talk stability in terms of the natural response. Okay? Forced response, what does it mean? It just means system will try to follow whatever the input is. The system response will be very similar to the output, whatever input is asking it to do. That determines the forced response. Okay? So what you saw was the two experiments you have done there. Did you see a forced response?
No.
It was mostly a natural response. Okay? So there was no forced response as such. So we talk about stability in terms of this natural response. So let's look at a few definitions. So we have already discussed this. The system is stable if natural response approaches zero and On the contrary, a system is unstable if approaches infinity and finally system is marginally stable
Marginal stability isn't really acceptable, though, is it? You don't
It's
really
not-
want.
you don't target marginal stability. You don't want your system to be marginal stable. Because that will, it may anytime, because you cannot really model a perfectly marginally stable system. You could model, but you may not be able to build one, which is perfectly marginally stable. And if you push it a little bit, it will become unstable. So you don't target, you don't discuss marginally stable systems.
Would that be like a sine wave? It's like a sine wave.
Sine wave or the response looks like a sine wave, but practically, what is a marginally unstable system?
So what is it?
Think about what is a marginally unstable system. Marginally stable or marginally unstable.
It gets to a certain time.
A pendulum.
Pendulum. A pendulum put in a vacuum
Yeah.
with no, frictionless this thing that will keep on doing that. Right? So that's a marginally unstable system. Any spacecraft in orbit is practically a marginal. It will keep on going, right? The response will not go to zero. So the natural response is neither decays nor grows. As time approaches. Okay. So one thing, what is the common factor or common terms of this definition?
The definition.
The definition, all these definitions are relying upon this
Natural response.
time approaches infinity. And you're right, Alex. It is also discussed in the context of natural response. The common denominator is this. Okay? Time approaches infinity. We discuss stability as time approaches infinity. Okay? So we have already discussed this. We have looked at this concept, right? You want to review this concept again? So tell me Let's look at this, okay? So let me discuss this a little bit here. Block diagram reduction. So this is what you need to know from chapter 5. Okay. So the first one is, let's discuss Cascade System. We have G1 of S, G2 of S. Okay. So here equivalent of above would be okay. So you just multiply the two blocks. This is cascade. Make sense?
But yeah, it does sound cool, but what is cascade?
Cascading is joining.
Joining, okay.
So when you join this is the equivalent system. This is G of S. You can say. Okay. And then you have this is the first one. Second one, parallel systems. You have G1, plus in the context of this, what you should know is this is a system. A block is a system. Got it? This line is what? The signal. Everybody with me? Understand systems as signals? Signals. And this is summing junction.
What's that?
I'll show you what that is. So here we have used the summing junction, right? You see this? Outputs cannot just cascade together. You will never see that. Alex, you're confused?
On the blocks that you drew on right, those go with the parallel systems.
No, these are for all. If you see here, there is no.
Okay.
Just the last one,
Okay.
that summing junction.
Summing junction is specific to this. So here, equivalent system would be G1 plus G2 Make sense, Micah? So if you have something like this, you add the two systems. If it is something like this, you multiply the two systems. Okay. Now you cannot just see the output cannot just be merged. Okay, that is not acceptable.
What do you mean?
So this is not okay. It's not allowed in this block diagram. Okay, so you have to have this. And you have to mention the signs. These are signs. So only whatever these signs, you are going to see that sign here. Okay, if it was negative, this one was negative, this one was positive, it would be minus G1 plus G2. If this was negative, then it would be G1 minus G2. Okay, so that sign you have to follow. And the third type of system, which we will use very often, is called the feedback system. Okay. So feedback system is a slightly more involved than these two. Although it is still very simple. They have G of S. And then you have H of S. This comes here. Minus plus. This is a typical feedback system. So what's happening here is, this is the plant being controlled. Okay, the input signal is going into this plant. The output signal is being fed back, so that the plant knows the difference. You understand? So this is like a sensor. It is generally called a transducer. So this could be a typical sensor. So what happens is, whatever you are sensing, what is transducer? Transducer is nothing but converting one physical quantity to another.
How does that have a negative sign?
Huh?
How does that have a negative sign?
So if you look at when you're tracking or when you're trying to follow a certain desired, you're trying to reach a desired output. You want to figure out how off you are, right, from the actual output. Right? So if you're trying to follow a line, you want to know how off you are. This will give you, this negative sign will give you how off you are.
It's not coming directly from the sensor.
It is coming directly from the sensor. You can think about that, it is directly coming from the sensor. it is transduced, it will tell you how off you are. For example, GPS, as you get closer and closer, that distance how off your distance is will get smaller and smaller, right? So that GPS, what is GPS? GPS is essentially a electrical device, right? It is all, whatever signal it is sensing, it's electrical. But what does it actually get converted to? Position, velocity, not velocity, but position. Right?
So negatives come from the sensor and positives come from the input.
Input, right. So if you are at that location, what will be your input?
If you were.
If you are at that location, your input should be practically zero. Because this difference is also zero. If you are off by certain this thing, then you actually say, okay, go this much distance. But that is what the feedback. So an equivalent system would be, now here you have to pay attention a little bit. I'll do some block diagram math. Don't take this, just look at it first. Okay? Micah, don't take down, just look at it. Tiffany,
I didn't like it.
you're always taking notes. So. Okay. I have not changed anything if you see here. Right? I broke the signal and just multiplied that by C of S. I haven't changed anything. Okay? Now what happens here is what signal is going into this is C of S into H of S. So this signal essentially gets multiplied by this. It's going through, it just gets multiplied. Okay? So it is C of S into H of S. Here we still have R of S, which is the input signal. And then this is still G of S. Our goal is, always remember, our goal is to find C of S over R of S. This is the transfer function. Okay? So this could be represented by G of S or sometimes T of S. Okay? So don't get confused. See, G of S or T of S just refers transfer function. It is output over input. Okay, here what is the transfer function? What is the equivalent transfer function?
G1,
G1, G2, that's it. G1 of S into G2 of S. Okay? So that is G of S. Here what is the equivalent transfer function?
G1 plus
G1 plus G2. So here we'll see what that equivalent transfer function is. Okay? So what you're going to see here is what signal is going in now? It is here it is R of S minus C of S H of S. You agree? I've just added these two signals. R of S is this. Okay? C of S is this. Now, let's look at it. C of S is what? G of S multiplied by R of S minus C of S H of S. Okay? I haven't changed anything. I'm just, this is equal to this whole thing into this. Okay? Now let's split this a little bit. C of S implies G of S, R of S minus C of S C of S, G of S, H of S. Okay? I just multiplied this, distributed this into this, minus this into this into this. C of S, G of S, and H of S. I'll take the C of S on this side. C of S plus C of S, G of S, H of S is equal to G of S, R of S. Okay. Now C of S, I take this common. This is 1 plus G of S, H of S equal to G of S, R of S. Right. What do we need? We need
C of S.
C of S over R of S. So if I just move this R of S to the left hand side and this whole thing to the right hand side, you're going to get C of S over R of S is equal to G of S divided by 1 plus G of S. Okay. So this is the equivalent transfer function. So if you see, what you see here is, if this is negative, this becomes positive. Okay, so if this is positive, this becomes negative. And sometimes this is sometimes referred to as, since there is a G of S already, we generally represent this as P of S. Okay. In other words, this is closed loop transfer function or closed loop control. You see, this is a closed loop or a feedback loop. Can there be open loop control?
Want to say.
You said what?
So I want to say.
Quincy, can there be open loop control? You're quiet, Quincy, today.
What you're saying.
I have very well. No.
There can be open loop control. Your toaster, for example, is an open loop control system.
So what?
The toaster.
That's why I want to say. But you said it's open loop because we put the bread in there and come back out. So okay.
It's time-based control. There is no sensor as such to sense how dark your toast is, right? Huh? If you want to design something like that, for example, if you, the first time you put your toast and the second time you put your toast, do you get the same?
Nope.
You mean if you put the bread back in it? You mean
If you immediately put your bread back in,
same toast bread?
yes,
That's not, you don't do that.
you don't get the same toast, right,
Even
on your bread the second time you put it.
It gets blacker over
Huh?
time. It gets darker over time.
if you put another piece of bread in the same toaster,
Right away, if you put another piece of toast,
no, it's gonna be darker.
it's going to be darker. So if you had a closed loop control, what would you get?
The same.
You will get the same color toast every time because it will sense what color it is.
That's the next generation of toaster.
Second time it will just keep that timer. It will just put it for 3 minutes or 1 minute, whatever, without taking into regard the output. It's not measuring the output. Okay. So let's finish with this a little bit.
Z has a question.
Stability. Yes, please. What's up?
Please don't erase the feedback.
Huh?
What about oven?
Huh? Oven is also it doesn't. Some have you seen these one? Just there is one button like potatoes or casserole.
Yeah, like a microwave.
If you see a microwave oven, ovens, you mean conventional ovens?
Like the convection oven.
The convection oven, they are closed loop control because they are always measuring the temperature and switching on. Got it? So here, tell me if this is 3 over s into s plus 1 s plus 2. So this signal is generally referred to as E of S or error signal. Okay, it makes sense. It is the error. It is the difference between input and output. Okay, so here you can say this is error signal. Whatever is coming out is error. You have minus plus. Is the above system stable? If this is asked, if you ask this question, okay, the first thing you are going to do is find P of S. P of S is equal to, this is C of S. This is also a unity feedback system. Why is it unity feedback system?
It's a what?
Unity feedback system. Unit feedback system. Because if you see this H of S is 1. Okay? So here if the question is the above system stable? First you have to do this. P of S is what? G of S divided by 1 plus G of S, H of S. Okay? Here H of S is 1.
How do you determine what H of S is?
If I put 1, will it change? Will this change if I put this as 1?
I'm not sure what H of S is.
Here, I did this, right? It does this math thing. That's the reason I told you, Michael.
Oh, H of S from over here.
Yeah.
Oh, okay.
Okay?
Yeah.
Okay. So this is, you can say this is a unity feedback system. So now what I do is, I just 3 divided by S into S plus 1 divided by S plus 2 divided 1 plus 3 over S into S plus 1 S plus 2. So this, if you simplify, you're going to get 3 divided by S into S plus 1 S plus 2 plus 2. Okay. And now poles of transfer function P of S are, let me give you the values. S1 is equal to minus 2.67, S2 and 3 minus 0. Okay. So this is a, if you see the polynomial, what order of polynomial is this?
Third order.
Third order, right? So how many poles will be there? How many roots will be there? 3 roots. This is the first root. Okay? And this is the second and third. These are complex roots. So is the system stable?
Complex. Yeah. According to the left, well, we're not using that anymore.
Is it stable? What did we say? Where does the, if you do the pole plot, where will be the roots be?
It's going to be a little bit on the J.
Huh?
Something going to be on the J, on the JW axis.
It won't be on the JW axis. When will it be on the JW axis?
It's also going to be on the left plane because of the -0.1.
So this, where will this be? So if you have 1, 2, okay, this will be somewhere here, right?
So it has one real root and one two complex roots.
Of course. Where will this be? This will be minus, the real part will be here, okay? And 1. So you see this, so this is negative minus 0.164 plus J 1.047, and this will be minus 0.164 minus J 1.04. Got it? Is the system stable or unstable?
System is stable.
It's
stable.
Quincy, you don't want to take,
I mean, according to the rule, it's stable. It would say it would be.
huh? What was the stability?
It's on the left hand side.
Tiffany?
I think it's unstable.
Why
Only-
so?
Well, I'm confused because I'm looking at that one in the lower half of the plane.
Did you guys look at your notes? The first thing we discussed was this only.
But I thought it had to be in the top left.
Did I say that?
That was my interpretation.
Why did you write it?
That was because the way I wrote it,
Why did you write it
I
that
took
way?
it to be like a second quadrant type of thing.
Why?
Because that's where I saw the words written.
Did you see LHP?
Let me see.
See, this is the reason I tell you not to take notes. Because you are not able to concentrate. It's a very simple thing. LHP. What is LHP? So left half plane. Everything is a left half plane. Left half is left half. Anyways, so this is a stable system. Okay. Make sense? It's a left half plane. If you see the first thing you note it down, that area you mark. Show me the area you mark.
This is what I wrote. This is what I'm talking
Right, so all of this area.
about. And is this what you had did?
Yes, I did that. So all that area, if the poles are in that left half plane, system is stable. Okay? So that it doesn't matter whether it's on the top or bottom, as long as it's in the, because see, complex poles will always be in pairs. So one of them will be here, one of them will be here. That's how complex poles are, or complex roots are. So is this clear? Is this clear? How this was done?
It's not going to be on the midterm tomorrow. It's not going to be on the midterm at the end of the week, right?
No, this is not going to be on the midterms.
2, 4,
Chapter 2, 3, 4 will be. I'll send you this thing today.
But for the midterm, we're allowed to use notes, a note for chapter 4. Right?
Yeah.
Yeah,
Like,
yeah, you can. Not notes, but formulas. You'll be given a formula sheet. I think I'll just give you the formula. Don't worry about preparing. Have you started preparing one?
Huh?
See?
Girl started.
Have you started preparing the formula sheet?
Yeah.
I haven't had chapter 4 yet.
Huh? You haven't got up to chapter 4?
No. Because,